analysis from position and velocity graphs and also acceleration graphs to look at how we can predict the motion of an object undergoing uniform acceleration using a series of equations known as the kinematic equations, our topic for 1.4. So kinematic equations, we state them here without any proof or any derivation. The reason being is that to derive the kinematic equations, you need to know calculus. So these are equations of motions for an equation of motion, better said, for an object undergoing uniform, meaning constant acceleration. So kinematic equations can be used to predict the motion of any object undergoing uniform or constant acceleration. If the acceleration is not constant, the kinematic equations cannot be used. So here are three kinematic equations. These two we cannot derive because they require calculus, while this one we can make a little bit of sense of. So let's go over what each of these variables mean prior to reviewing the equations. So x naught, the little zero subscript is what we call a naught, indicates initial position. X indicates our final position, while v naught indicates our initial velocity, v indicates our final velocity, a is our acceleration, and t is our time. So thus these equations read that the final position of an object is equal to the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. The time squared part, the acceleration here is not squared, it's only the time that is squared. This equation states that the final velocity equals the initial velocity plus the acceleration times time. We can actually make sense of this equation if we recall that acceleration times time gives us the area underneath an acceleration versus time graph and thus our change in velocity. So this equation is actually our final velocity equals initial velocity plus our change in velocity. Final equals initial plus the change. Something that we should be familiar with from algebra. And this last equation states that the velocity squared equals the initial velocity squared plus 2 times our acceleration times x times our final position minus our initial position. So to use the kinematic equations, here are the steps that we're going to follow. Because we do have three equations, we need to determine which of the three are best used for a specific scenario. So steps to follow is that we're going to write down our known information, abbreviate as you wish. You can call it U, you can call it K or I, whatever you wish to abbreviate your known information as, okay? So then we write down our unknown information. I abbreviate this as a U because of the unknown. And then the critical step is that we're going to use our knowns and unknowns to determine which equations to use. So here it's important to make sure that you have all variables lined up with the correct numbers, so that x is matched up with position, a number for position, v is matched up with a number for velocity, and so on and so forth. And thus you must also make sure you're familiar with your units for position, velocity, and acceleration. And the fourth step that we're going to do is we're going to solve our equation for our unknown quantity. So let's look at what this looks like in practice. Oh, I forgot a little point right here. So in physics, it's customary and easier to take the initial position x naught to be 0, since that is where we start at. And also that the object, unless otherwise specified, will head to the right. So it's always customary to take these two things, that the initial position is 0, since that's where we start measuring from, and that the object, unless otherwise specified, will head to the right. So let's look at an example, okay? A car is moving at a speed of 60 kilometers per hour when it brakes to rest so as to not to run a stoplight. If the brakes act at 10,000 kilometers per second squared, an extreme case for an extreme scenario before coming to rest, how far will the car travel? Please neglect the seconds per second squared. It should actually be hours squared in order to match up with the unit of time right here. This is just a typo on my part. So the first thing that we're going to do is we're going to write down my known. So I abbreviate that as a K. We know that x naught is 0 kilometers, since that's where we decide to start measuring at. We know our initial velocity is 60 kilometers per hour, okay? We know our final velocity is 0 kilometers per hour, okay? Again, I messed up with the units here. I'm used to using meters per second. What's important to note is that the final velocity is not explicitly stated in the problem. It does not state that we come to 0 miles per hour, but it does state that the brakes act at a certain rate before we come to rest, indicating that our object is going to arrive to rest at the end of its travels, telling us that our final velocity is 0 meters per second. And then lastly, our acceleration is negative 10,000 kilometers per hour squared. Again, forgetting the second squared part and replacing with hours. The reason being is that if our object is heading towards the right, aka a positive velocity, our acceleration must be heading towards the left in order to slow down, thus a negative acceleration since it's heading towards the left. So as a result, we move on to step 2. My unknown is the final position. How far will the car travel? Again, it doesn't explicitly state to find our final position, but indicating how far our car travels insinuates that we're looking for a final position. Again, please make sure you do not confuse units. So note here that all my numbers match up with the units, with the symbols that we're looking at. So position of 0 kilometers matches up with x naught, initial position. Kilometers per hour matches up with velocity in terms of units, and kilometers per hour squared matches up with acceleration in terms of units. So it's important to make sure you're able to place the units in their proper spots when writing down your known information. So now we move on to step 3. Based on my knowns and unknowns, the best equation to use is v squared equals v naught squared plus 2 times the acceleration times x times our final position minus our initial position. We can't use the first equation or the second equation from the prior slides because those equations require the use of time, and the problem does not state a time interval. We'll see actually the next slide that we could calculate a time interval, but doing so is a little bit more difficult, and it's a little bit less efficient than using this equation right here. Okay? So we proceed to solve for our equation. Our final velocity is 0, and our initial position is 0, so we can cross these guys out and make them 0, giving us 0 equals v naught squared plus 2ax. Now we solve for x, so we subtract v naught squared from both sides, and then we divide by 2a to get that our final position is negative v naught squared divided by 2a. Notice that the negative is outside of the squared here. The negative is not inside of the squared, otherwise there would be parentheses. So now we plug in our known information. We have 60 kilometers per hour divided by 2 times 10,000 kilometers per second squared. And then we also have this negative sign right here. If we simplify this result down and calculate our numbers, we get that x equals 0.18 kilometers. Thus telling us that at the ends of the interval when the car comes to rest, the object will have traveled 0.18 kilometers. An alternative solution is we could use one of the equations to find time, and then subsequently use another equation with the time that we found to find our final position. So what we could have done here is we could have recognized that we know our initial velocity, we know our final velocity, and we know our acceleration, and thus we could have used that with the second kinematic equation to find time. V is 0, V naught is 60, and A is negative 10,000 kilometers per hour squared. And again, I totally messed up here because this says kilograms per second squared. Ugh, not good. So solving for t gives us t equals 0.006 seconds. Now we know that we're looking for the final position, so we can plug t into the equation, the first kinematic equation, to solve for time, or excuse me, solve for our position. So x equals x naught plus v naught t plus 1/2 at squared. So as a result, x naught cancels out, our initial position is 0. We have v naught is 60 kilometers per hour. We have our time is 0.06 seconds, and then we have negative 10,000 kilometers per hour squared. Now I got the units correct, woo, all the way down here. Multiplied by 0.006 seconds squared. Again, the time is squared, nothing else in this last term is. So it's a time squared multiplied by acceleration multiplied by 1/2. Doing this will give us, once this bar disappears, the correct answer of 0.18 kilometers as we found previously. So you could have used this method, but again, it's always most effective to identify one equation that you can use instead of having to use as many equations as possible. Lastly, we get to average velocity. This equation is not on your equation sheet, but it's not that difficult to remember. So if we want to find the average velocity, provided the initial velocity and final velocity of an object, we apply the average equation from mathematics. The sum of all our values is divided by the number of values that we have is equal to our average. So here, if we have two values, our initial velocity and our final velocity, then the number of values we have is 2, so our average is going to be the initial plus the final divided by 2. This can be used to determine the average velocity provided initial and final velocity. So if you're asked to determine average velocity over an interval and you're given initial and final velocity, this is specifically where you should use the equation at, okay? You will not use this equation for any prior scenarios, nor will you use any prior equations for a scenario of average velocity, because all the prior equations do not contain a term for our average velocity. This is the only equation for average velocity that we have that we have in physics. And this covers the basis for kinematics.